Hi, my name is Ty, and today I'll be talking about improved algorithms for lowering approximation from sparsity. And this is based on joint work with David Woodruff, who's my advisor at Carnegie Mellon University. So I'll start off by defining the low rank approximation problem. So in this problem, we're given as an input an n by n symmetric matrix A, as well as a rank parameter k. And our goal is to find a rank k matrix A hat that approximates A in some sense. And usually, this A hat is found by finding the matrix A that minimizes, finding the matrix X that minimizes A minus X in some norm over the space of all rank K matrices X. Here, the norm can be chosen to be the Frobenius norm, spectral norm, or the entry-wise LP norms, or a variety of other selections. But for the purposes of this talk, we'll be focusing on the spectral norm. Now, in order to discuss our results, I'll introduce the singular value decomposition, or the SVD. So in the SVD, we can take a symmetric matrix A and write it as the product U times sigma times U transpose, where U is a matrix that has orthonormal vectors, which are known as the singular vectors along its columns. And sigma is a diagonal matrix that has the singular values down its diagonal. Now, associated with the SVD is a natural matrix AK, which is a rank K matrix that can be obtained by taking just the top K vectors of the singular vectors, as well as the top K singular values. And by the Eckart-Young-Mirsky theorem, this is known to be optimal for Frobenius or the spectral norm lowering approximation problem. Now, in terms of algorithms, it's known that the exact SVD can be computed in time n to the omega, where omega here is the exponent of matrix multiplication. Now, if we're willing to settle for approximations, then it's also known that an approximate SVD can be computed in O of NNZ of A times K over square root epsilon time. And here, NNZ of A refers to the number of non-zero entries of A, and epsilon is an accuracy parameter. And here, the notion of approximation is that we want to output a matrix A hat such that A minus A hat in the spectral norm is at most 1 plus epsilon times A minus AK in the spectral norm, which is also the same thing as 1 plus epsilon times sigma k plus 1. So what this means is that A hat will remove all the top singular values of A, except for those that are at most a 1 plus epsilon factor larger than sigma k plus 1. Now, this NNZ of A times K over square root epsilon time has been a long-standing barrier. And a natural question that we could ask is, can we get an algorithm that's faster than this if we assume that the top K singular vectors are sparse? So what do I mean by sparse? So what I mean is that if I look at AK, the optimal rank K approximation given by the SVD, then the top K vectors will be S sparse, meaning that these top K singular vectors only have at most S non-zero entries each. Now, our main theorem in this setting is that if I am guaranteed that A has top K singular vectors that are all S sparse, then we can compute an approximate spectral lowering approximation in time NNZ of A over square root epsilon plus lower order polynomial terms that depend only on S, K, and 1 over epsilon. So if I look at the dominant term here, which is NNZ of A over square root epsilon, this means that if the top K singular vectors are sparse, then we can save a factor of K over the best known spectral lowering approximation algorithm. Now, this is the result that I want to prove, but before I do that, I want to introduce some of our other results in the sketching model. So in order to do that, let me briefly introduce the sketching model. So in this model, our input matrix A is observed through T linear measurements. And by that, here's what I mean. So we first get to choose query matrices Si, which is an n by n matrix for I from 1 equal T, 1 through T. And these query matrices can be chosen to be random. And then after I choose these query matrices, I'll be able to observe the inner product between Si and A from I equals 1 through T. And finally, after I observe these linear measurements, I can I compute my output as a function of these queries that I observe. And here, The complexity measure that we're trying to optimize is the number of measurements t. Now, in this model, low-rank approximation has been studied in the past in the Frobenius norm, and it's known that nk over epsilon measurements is necessary and sufficient for this problem. Now, again, we could ask whether sparsity could improve the situation. And this time, we're going to be using sparsity in a slightly different way, where instead of assuming that A has some natural sparsity attached to it, we instead change the optimization problem so that we explicitly search for an S by S matrix that approximates A. So more formally, we want to find an A hat that minimizes A minus X, where X ranges over rank K matrices that are supported on an S by S submatrix. Now, in this setting, we show a variety of results and trade-offs, where we can solve this problem in T measurements, where T can be taken to be Sk over epsilon squared, if we allow for the use of an exponential time algorithm, but we get to output a genuinely S by S matrix A hat. Now, this exponential time might be undesirable, but we still get a very small measurement complexity of Sk over epsilon squared. So note that this actually doesn't depend on n in a polynomial way. Now, this exponential time is undesirable, so our second result is that if we allow for a slightly increased number of measurements, so if we use S squared times K squared over poly epsilon, then we're actually able to get a polynomial time algorithm with the additional caveat that we output a relaxed sparsity. So our output matrix is Sk over epsilon times Sk over epsilon. And finally, we can actually obtain a further improved measurement complexity with polynomial time if we allow for an additive error instead of the earlier relative error notion that I mentioned. So this is all I want to mention for now for these results, and I'll refer you to our full version of our paper for additional details. So the rest of this talk, I'll be coming back to this result on computing a spectral low-rank approximation in NNZ of A over square root epsilon time for sparse singular vectors. So as an overview of how we take this approach, I'll first reduce our tasks to finding the support of the singular vectors. And once I do that, I'll show you an NNZ of A over epsilon time algorithm for this reduced task of finding the support. And then I'll show you how to improve this to NNZ of A over square root epsilon. Now, one thing to note is that this improvement from the dependence of epsilon to square root epsilon is kind of standard in previous works, but in our work, it's actually a very non-trivial part of our algorithm. So it's not just a classical use of acceleration using Chebyshev polynomials. So without further ado, I'll get into the first step, which is the reduction to finding the support of the singular vectors. So the first thing to note here is that the top k singular vectors are all actually supported on a set of at most s times k coordinates, where I have s coordinates for each of the k sparse singular vectors. Now the claim is that if we can then find a small set S that contains the support of these top k singular vectors, then what we can do is we can just restrict to these coordinates and then solve low-rank approximation on this submatrix, on this restriction. Now, to briefly see why this is the case, so consider this A bar S by S, which denotes the restriction, the submatrix. And what you'll notice is that if I consider the top k singular vectors, ui, then A times ui in the 2 norm is exactly preserved by restricting to the submatrix. And this is basically because ui is just 0 anyway outside of the support. However, if I consider any other vector, then what happens is that the value of ax in the 2 norm can only decrease since I'm just throwing away mass. So what this means is that the top k singular vectors are preserved under this restriction, while the rest of the singular components can only decrease. So that's the intuition for why it reduces to finding the support of the singular vectors. Now I'll move on to the NNZ of A over epsilon time algorithm. So the main idea for this step is to just use power method. So the first thing I'm going to do is I'm going to go ahead and show you the pseudocode. So the first thing I do is I'll set a parameter q equal to 1 over epsilon, and I'll initialize a vector x which is going to be my iterate, by a single Gaussian vector G in n dimensions. And then for q iterations, what I'll do is I'll repeatedly set x equal to a times x. So this essentially accumulates the product a to the q times g. And note that each one of these matrix vector multiplications takes time n and z of a, and I'm doing this for 1/epsilon iterations, which gives me the running time. And then finally, what I'll do is I'll put the coordinates that correspond to the O of sk largest coordinates of x in absolute value. Now, this is the algorithm, and let's see why this works. So first, I'm gonna think about a to the power q, and the first thing I'll do is I'll write this in its SVD. So this is the same thing as u sigma u transpose to the power q. And if I expand this matrix product out, you'll see that the u and the u transpose cancel out because u has orthonormal columns. So this will give me u times sigma to the power q times u transpose. Now, let's think about what this sigma to the power q does to the singular values. So suppose that I have singular values, let's say 3 of them, that are each separated by a factor of 1 plus epsilon, and this is the singular values of a. Now, what happens when I take the qth power of these singular values is that each of these 1 plus epsilon factor gaps are then boosted to constant factor gaps. So what this means is that, for example, if I have any singular value that's a 1 plus epsilon factor greater than sigma k plus 1, then these are all going to be a factor of a constant factor larger in the matrix product a to the q. So with that in mind, let's go ahead and see what happens when I find a to the q times this Gaussian vector g. So first, I'll write a to the q in terms of its SVD, like I did before. And let's first see what happens to this first matrix vector product. So here, notice that u transpose has orthonormal rows. So what this means is that if I multiply this matrix by a Gaussian vector g, then what I'm going to get back is another Gaussian vector, a vector that's distributed as a Gaussian that's only in r dimensions, where r is the rank of the matrix. And then next, I'll multiply this Gaussian vector by this diagonal matrix sigma to the power q. And what this gives me is a different Gaussian vector where each of the coordinates is scaled by sigma I to the power q. And since these Gaussian entries are basically just like sign flips, they don't really affect the order of magnitude of these entries. I'm just going to throw this away for simplicity. And then finally, I'm going to look at this matrix vector product. And what this does is it essentially gives you a linear combination of the singular vectors of A, where the ith singular vector is scaled by a coefficient that's roughly on the order of sigma I to the power q. And again, recall that the any singular value that's larger than a factor of 1 plus epsilon and sigma k plus 1 is actually scaled a constant factor larger than anything below sigma k plus 1. So as a result, all I get back is this vector where I'll see all these coordinates that correspond to the top k singular vectors as being boosted by a factor of a constant factor. So what this means is that I can just read off of these top sk coordinates that are the largest in this resulting vector, and this will give me my support superset S that I want. And that concludes the n and z of A over epsilon time algorithm. Now, in order to boost this to an n and z of A over square root epsilon time algorithm, the initial thought might be to just use Chebyshev polynomials. So let me go over why what this idea is and why it doesn't work. The idea for using Chebyshev polynomials is that I want to replace the use of a to the power q with t to the a, where t is some degree square root q polynomial instead of a degree q polynomial. So the idea is to choose t so that t of x is at most 1. So whenever x is an entry that's at most the k plus 1 singular value, and whenever x is at least 1 plus epsilon times the k plus 1 singular value, then I want the value of the polynomial to be at least a constant. Now, so this looks something like this. And this has worked in the past, for example, for standard low-rank approximation. But what's the problem here? The problem here is that t depends on sigma k plus 1. And we don't know the value of sigma k plus 1, which means that this approach cannot work, at least as is naively. So what's our fix? So the first thing we do is that we know that we can still run the previous algorithm if we set epsilon equal to square root epsilon instead. And this will still get us some support superset S that gives us some sort of approximation. Then what we'll do is we'll use this support superset S to obtain a rank K approximation A hat of this submatrix restricted to S. And then next we'll show that we'll be able to get a 1 plus square root epsilon approximation to sigma k plus 1 using this rank K approximation. And then finally, once we have this 1 plus square root epsilon approximation to sigma k plus 1, then we can actually exactly get sigma k plus 1 up to a factor of 1 plus epsilon by making 1 over square root epsilon guesses. So this is just by noticing that 1 plus epsilon to the power 1 over square root epsilon is around 1 plus square root epsilon. Now, the non-trivial step here is going to be the third step. So this is the step that I'm going to go ahead and explain. So let's first plot the singular values of A as so, where I'm going to normalize the k plus 1 singular value to be 1. And let's also plot the singular values of our submatrix A restricted to S by S. And the first thing that you'll notice is that by the Cauchy interlacing theorem, the singular values of the submatrix is always at most the singular values of the original matrix. And another thing that I want you to notice is that any singular value above 1 plus square root epsilon is actually going to have very good, they're going to be very good estimates of the singular values of the original matrix A. And this is because as long as the singular value is at least 1 plus square root epsilon, then we'll actually successfully recover the support of the singular vectors. On the other hand, if we look at any singular value that's at most 1 plus square root epsilon, then we may have, it may happen that the singular values of the submatrix are significantly smaller than those in A. Now, in order to obtain our 1 plus square root epsilon approximation, we basically really want to find this index I, which is the largest index, such that the singular value sigma I is larger than 1 plus square root epsilon. So once we find this, we'll basically be able to have like a reasonable estimate of sigma k plus 1 within a factor of 1 plus square root epsilon. But the problem is we still don't know how to find this index sigma I. So what's the idea for getting around this problem? So the idea is that we want to find singular value upper bounds that approximately match these lower bounds. So let's see what this means. So first, consider the best rank I approximation to our submatrix A bar S by S. Then suppose that we calculate the operator norm of A minus this approximation. And know that this can be done in NNZ of A over square root epsilon time, since we're just computing singular values, a single singular value. Then this upper bounds the quantity, the minimum over rank I matrices X of A minus X in the spectral norm. But you'll notice that this is actually just this the I plus 1 singular value of A. So what this means is that the spectral norm of A minus our rank I approximation to the submatrix serves as a valid upper bound on the singular values of A. So with this idea in hand, this leads to the following observation. So if we plot the values A minus the rank I minus 1 approximation of our submatrix and the operator norm, then these all give upper bounds on the singular values of A, while being very close to these values up to a factor of 1 plus epsilon whenever the singular value is at least 1 plus square root epsilon. So what we'll notice is that anything above this 1 plus square root epsilon line, these upper bounds and lower bounds will match. So this leads to the following algorithm. So what we're going to do is we're going to binary search for the smallest index such that the smallest index I, such that the ith singular value is the smallest singular value that's at least 1 plus square epsilon. So let's say we start at index k over 2, and we compute the singular value upper bound, as well as the lower bound using Cauchy interlacing theorem. And if we see that these two values are within 1 plus epsilon factors of each other, then we'll search for a lower index. So let's say we look for the singular value corresponding to 3k over 4. And so we'll compute the upper bound and the lower bound. And this time, if we see that these two upper bounds and lower bounds are further than 1 plus epsilon, then we're going to search for a higher singular value. So let's say we search here, we find the upper bound and the lower bound, and if they don't match, we find the upper bound, lower bound for the next index. And using this binary search algorithm, we'll be able to find this index I star, which is the smallest singular value that's at least 1 plus square epsilon. Now, once we have this in hand, we can actually use the same trick as before to compute the singular value that's right under this. So if I compute A minus the I starth rank I approximation of the submatrix, then this will give me a valid 1 plus square epsilon estimate of sigma k plus 1. And this concludes the algorithm, since this is the last step that we needed. So to conclude, in this work, we showed an NNZ of A over square epsilon time algorithm for spectral low rank approximation for matrices with sparse singular vectors. And importantly, this removes the factor of k over the previously known NNZ of A times k over square epsilon algorithm for general matrices. And in terms of techniques, our algorithm involved a combination of power method, Chebyshev polynomials, and a clever binary search, which used efficient singular value estimate certificates. And finally, one very important open direction that we leave open is that of designing a robust version of this algorithm that allows for example, like finite precision errors, as well as singular vectors that are not exactly sparse. And finally, our paper also includes other results that give improved space complexity for streaming algorithms for related sparse low rank approximation problems. Thank you.